Good morning. We will concentrate next on the vertical climb. In a vertical climb, assume that the helicopter is climbing with a rate of climb c. We can demonstrate that the air is accelerated at the level of the rotor with a c plus induced velocity, and that down in the wake, the wake is contracting and the velocity is c plus twice induced velocity in hover. In an equilibrium, assuming that the drag of the fuselage is almost zero, thrust equals weight. For the actuator disk theory in vertical climb, we can use the same relations as for the hover. We can demonstrate that the thrust equals with mass flow rate multiplied with twice the induced velocity at the level of the rotor, that the mass flow rate is given by the mass flow rate passing through the rotor, and that the power is thrust multiplied by induced velocity. So, in a vertical climb, the velocity in the wake is twice the induced velocity at the level of the rotor. In a blade element theory, assume exactly like in hovering flight that we are representing a blade element. Assume that we see the tip-off plane, and then again, the blade is having a perpendicular velocity, omega r, a tangential velocity, omega r, and a perpendicular component of the velocity, c plus vi. Assume that c plus vi is usually much smaller than the rotor tip speed, omega r, and induced velocity is perpendicular to the tip-off plane. It follows that the thrust force, which is the projections of the forces on the blade element, is also approximately equal with the lift force that exactly like we have demonstrated for hover. The power then is the power needed to counteract the drag forces, and the drag force multiplied by omega r. So it is a climbing power plus an induced power plus a profile drag power. So the total power can be obtained integrating along the radius and along the azimuth for the blades, and we end exactly like in hover with the induced power and the profile power. We have as extra the climbing power. So if we want to go from hover to a vertical climb, we need to apply the collective pitch and transition to vertical climb till we obtain a stable vertical climb. If we go back to the induced power, to the actuator disk theory, we can rewrite the actuator disk theory for the vertical climb and obtain an equation for the induced velocity. Recalling the expression of the induced velocity in hover, T over 2 rho PR squared, we obtained the induced velocity for the vertical climb. As the power induced is a factor k multiplied by the ideal power, we have the final expression of the power induced as a function of the k, of the climbing velocity and the induced power in hover. As in most cases, the vertical climb rate is much smaller than the induced velocity in hover, it follows that the induced velocity in power in climbing flight is actually induced velocity in hover minus a coefficient kwc over 2. Therefore, the induced power in climb is lower than in hovering flight. So we need less power when we are climbing. Something else. For the profile power, we need to apply the same formula as we apply in hover. So the profile power is an integral from around the radius multiplied with the number of blades from the drag forces on the blade. And if we define the blade solidity, we can express this profile power. Recalling the formula for the thrust that we have derived at hovering flight, it means that if we know the medium drag coefficient on the blades, we can define for a different tip speed on the helicopter the profile drag coefficient, and if we have the profile drag coefficient, we can calculate the profile the power profile that we have in the vertical climb, exactly like in hovering flight. Now, estimating the rate of climb. The total power is the power to climb plus the induced power and the profile power. Now, if we assume K the loss coefficients of 1, you would see that the rate of climb is actually twice the total power minus power to hover divided by the weight. Therefore, the power excess in hovering flight is in such a way that the rate of climb is twice the value that would be estimated from the excess power in hovering flight. So it is not only the excess power in hovering flight, but it is twice the excess power estimated in hovering flight. This ends the main derivation of the performance for the climbing flight. So the most important things is that we can apply the same theories as in hovering flight to the forward flight, that the wake is contracting and that rate of climb, it is actually twice the excess power that we need in hover flight.